Things are going all right? Good. All right. Well, let's chat a little bit more about matrix arithmetic stuff. So last time we talked about adding matrices, we talked about subtracting matrices, doing scalar multiplication of matrices, and when matrices are equal to each other. So let's look at this last part here. We didn't get to that. We have E plus 3F. In order to be able to add or subtract matrices, what has to be true about the matrices themselves? Same dimensions, right? Do E and F here have the same dimensions? Yes. What are the dimensions for E and F? 2 by 1. Remember when we say the dimensions, we always do rows by columns, right? 2 rows, 1 column here. Okay? So when we want to do this one, E is the matrix 4, negative 3, and F is the matrix 9, negative 4. What should we do first? Yeah, we should do that scalar multiplication, right? How do we do scalar multiplication again? Yeah, basically it's like a distributive property, right? We'll take that 3 and we'll multiply it by each entry. 3 times 9 gives you 27. 3 times the negative 4 gives you the negative 12. And now when we add the two matrices together, how do we add again? Yeah, basically we're just matching the corresponding entries, right? And add them together. So in the first entry we'll have a 31, and the second one we'll get a negative 15. This okay? Is do. All right. Look familiar from what we did last time? Now, one of the things that we can do is kind of a practice with this is we can also solve what's referred to as a matrix equation. If these were just if this was just 2x plus a equals 4b, and I asked you to solve for x, not worrying about the fact that they're matrices, but just say there were numbers, what would you do to solve for x? What would you do first? Yeah, I'd move a over, and then we would divide both sides by 2. So that we can do the exact same thing here with matrix equations, right? We could still move the a over and then divide by 2. Dividing by 2 is the same thing as multiplying by a half. So I'll write it as 1/2 times negative a plus 4b. I know what my a and my b are up here. I need to shrink it a little bit so I can write them down. A was the matrix negative 2, 1, 3, 4, 0, negative 1. And B is the matrix 4, 1, negative 2, 5, negative 1, 3. Does that look like something we can simplify, knowing what we know now with matrix arithmetic? Notice again, from here to here, this isn't anything new that you've done, is it? Right? You work with variables and solve for a variable before. That's nothing new here. The new stuff is just trying to get the answer simplified. Looking at the inside there, we should probably distribute those numbers through first, right? Do the scalar multiplication. So the first thing I'll do is distribute the negative through everything. So you would have 4, negative 1, negative 3, negative 4, 0, positive 1 there. Oops, that's a 2. I don't know why I wrote a 4. Everybody okay with that? Just taking the negative and distributing it throughout everything? What do you get in the second one when you multiply by the 4? Mm-hmm. Yep, good. So again, we take the scalar and just multiply the number. We call it a scalar. We take the number and multiply it through each entry, right? Then when we add, what do we get when we add those things together? Good. Okay. Good. All right, we just add each entry. And again, notice we had those in parentheses, right? So that was why I did the addition before we multiply by the 1/2. And then finally, we'll take the 1/2 and multiply it through everything. We'll have a 9, a 3/2, a -11/2, an 8, a -2, and a 13/2 when we're done. That's okay? Yes, you're good? Thanks for the thumbs up. I appreciate it. Is okay? We good? Awesome. All right. So that's addition and the subtraction and scalar multiplication. We're also going to do matrix multiplication. Now, matrix multiplication is a little bit strange. We define it this way because of different things that we want to be able to use matrix multiplication for. So it's not just simply like addition and subtraction, we make corresponding entries and do the operation, right? That's not how we multiply matrices together. So the first thing, in order to be able to multiply matrices together, something has to be true about this number here and this number here, okay? So if I want to multiply A times B, that N number there, the number of columns in A, has to be the same as that P. So we need the N to equal P, okay? So to write it this way, I'll just write out in words. In order to compute A times B, we need the number of columns of A to equal the number of rows of B. When we're done, we get a matrix that has the size the same as the number of rows of A and the columns of B. So in this case, we get an M by K matrix when we're done. So the number of rows in the product is the same as the number of the first thing, and the number of columns in the second product is the second thing. Okay? I know it seems a little strange. So how do we end up actually having to do this? Well, I'm going to do basically one product, one particular product here to show you how it's done, and then we'll talk about how it gets matched up in the other examples here. Okay? So if I had, maybe my A vector here, or my A matrix was a 1, a 2, and a -4. And then my B matrix I'm going to write as a column. And to say we have a 3 and a -3 and a 2, for for lack of better, doesn't matter what the numbers are. All right, so I'm treating this one as my A and this one as my B. Okay. What dimensions does A have? 1 by 3, and B has 3 by 1. So my number of columns of A match my number of rows of B. Okay. When I'm done, according to what I told you earlier, what size matrices you end up with? So it's the number of rows in A and number of columns in B. So what we end up with. How many rows does A have? Yeah, 1, and B has 1 column, right? So I should end up with a 1 by 1 matrix. I should end up with a single number when I'm done for this one. Okay. Here's how you do it. I'm going to write it with brackets because it is supposed to be a matrix here. Here's how we do it. And I like to do it kind of in my brain visually. You're going to take this row and you're going to match it with this column. Okay? And we're going to multiply corresponding entries. So I'll do 1 times 3. I'll do 2 times a negative 3. And we'll do a negative 4 times a 2. Okay. Now I just said it was a 1 by 1, right? So I have to get a single number when I'm done. Here's what you do with those 3 numbers. You add them together. Okay. So when you multiply A times a B, you're always going to match a row with a column and do this product sum thing, right? Multiply, add, multiply, add, multiply until you're out of entries. That's how we create each entry. Okay, so let's do a bigger example. Pardon me, sorry. In this example, we're going to do B times C. All right, so first, do these have the right sizes in order to be able to be multiplied? Yeah, the columns, how many columns does B have? How many columns does B have? 3, right? And then the number of rows in C is 3. Okay, so it has the right size, right? Okay. What size is the answer going to be? It'll be a 2 by 2, right? B has 2 rows, C has 2 columns. So the answer will be a 2 by 2. Okay. So how do we fill out each of those entries? Well, it's the same idea. The first thing we're going to do, I'm going to match row 1 with column 1. I'm matching row 1 with column 1 gives me the row 1, column 1 entry. Okay. So I'll have 4 times 2 plus 1 times 0 plus negative 2 times negative 3. So, and in my brain, at least I visualize it as take this and rotate it, right? I'm matching it up. Okay. And they all need to line up. 4 lines up with the 2, 1 lines up with the 0, negative 2 lines up with the negative 3. If they don't line up, if you don't have the same number of entries, you can't do the multiplication. Okay? All right. We'll simplify it in a second, but are we okay with that entry, how I got it? Okay. Let's do the next one over. Let's do, bless you. Let's do row 1 and match it with column 2. I'm matching row 1 with column 2, so it's going to go in the 1, 2 spot. Okay. What multiplications are you going to do? We're still matching with the row 1. Yeah, we're going that way. So it'll be 4 times the negative 1 plus the 1 times the 6. Yep. And the negative 2 times the 2. So again, in this one, I'll circle them this time. We're matching row 1 with column 2, so it's going in the 1, 2 spot. So what's going to go in the 2, 1 spot? Two, 1. Still have 2, 2 circled. 2, 1. What's going to go in the 2, 1 spot? 5 times 2 plus, good, time plus, good. So again, visualizing it, I'm taking this row and matching it with that column, right? Making the entries line up. What's the last one going to be? Okay, 5 times negative 1. Negative 1 times 6. And 3 times 2. Do we see where those are coming from? Now, if we simplify, we get 8 plus 0 plus 6 gives us 14. Negative 4 plus 6 is positive 2. Minus 4 gives me a negative 2. 10 minus 9 is 1. Negative 11 plus 6 is a negative 5. Questions on that? Okay? Let's do the next one. Oops. We're going to do C. We're going to reverse it. We're going to do C times B. Are we okay to multiply these two together? Yep, no issues there, right? We can multiply them without any problems, right? Okay. What size matrix are we going to get when we're done? Careful. This one's going to be a 3 by 3, right? Because remember the dimensions when you're done are the number of rows in the first one by number of columns in the second. So notice that you're going to get two different matrices. So the order matters when you multiply matrices, by the way. Okay? You may get different answers when you reverse the order. That's different than real numbers, isn't it? When you multiply real numbers, you get the same answer. It doesn't matter how you multiply. Matrices, it's not true. You can get different answers. Okay. All right. What are we going to get for the upper left corner? What do you have to compute to get the upper left corner? Two times 4, and add. Remember, we go across the row and down the column at the same time. So it'll be negative 1 times the 5, right? Do we see where those are coming from? We're matching the row with, and this is why the number of columns have to match the number of rows here to be able to multiply. We're matching the row with the column, right? So 2 times the 4, negative 1 times the 5. Going across to the next row, how do we compute the next one over? How do we compute the one that's in the 1, 2 spot? Two times 1, negative 1 times negative 1. Okay. Again, we're matching this row with that column, right? Row 1 with column 2 goes in the row 1, column 2 spot. Next one over. 2 times negative 2 plus negative 1 times 3. Good. Do we see where the first row came from? Is this okay so far? If it's not, now's the time to ask. All right. Work on the next 2 rows. You should have 2 more rows to fill out. Do those for a minute, and we'll chat about it. Okay. Ready to talk about it? So I went ahead and wrote in the entries. So again, as we go across the second row here, we would take the 0 times the 4, the 6 times the 5, and add it together to get that first entry in the second row. Because again, we're matching row 2 with column 1. Notice as you go across the rows, I'm going to match those same 0 and 6 with the other 2 columns, right? So the next one's going to be 0 times 1, 6 times -1, match there, right? And then 0 times -2 and 6 times 3 for that last one over here. Notice, if you look in your rows, as you go across your row, those first numbers in your products don't change, do they? I use the same numbers all the way across. So in that last row, I would match -3 and 4 and the 2 and the 5 and then add. Do the -3 and the 1, the 2 and the -1 and then add. -3 and -2, 2 and the 3 and then add. Are we okay with how these are getting matched up? Yeah. Okay. And then if we just simplify at that point, 8 minus 5 is 3, 2 plus 1 is 3, Negative 4 minus 3 is negative 7. 0 plus 30 is 30. 0 minus 6 is negative 6. 0 plus 18 is 18. Negative 12 plus 10 is negative 2. Negative 3 plus negative 2 is negative 5. 6 plus 6 is 12. Assuming I did all my arithmetic right in my head. That okay? All right. What about the next one? What do you think when I write d squared? What do you think that means? Yeah, it means d times d, right? So the matrix D is 2, negative 4, 1, 6. And I want to multiply by 2, negative 4, 1, 6. Multiply it by itself. That's what squaring means, right? Now, in order to be able to square a matrix, what better be true about that matrix, do you think, about as far as rows and columns? They have to be the same, right? And we actually refer to those types of matrices as square matrices. Okay? So in order to be able to square a matrix, it has to be a square matrix. It has to have the same number of rows and columns. What are we going to get when we multiply these two together? What's the upper left entry going to be? And then negative 4 times the 1. The next entry in that first row will be okay. And then good. Second row will be okay, and plus 6 times 1. And the other one will be good. Just like we did the other ones, right? There's nothing any different about squaring a matrix than it was by multiplying two other matrices together. And if we simplify the arithmetic here, 4 minus 4 is 0. Negative 8 minus 24 is negative 32. 2 plus 6 is 8. Negative 4 plus 36 is positive 32. Questions on that one? Is okay? Are we comfortable with multiplying these things with these definitions? All right. I'm going to leave the next couple for you for practice, and then I want to go on to the idea of writing a systems of equations as a matrix equation. This is going to lead us into the next section. So the idea here is to be able to rewrite a system as a product of matrices equals another number. All right. So, pardon me. Goodness. Okay. So the idea here is to try to recognize what's going on in, or basically on the left-hand side of the equation here, looking at this piece here. Notice when we were doing these other products, let me go back up. When we did these products, notice that we were multiplying, when we did the first row times the first column here, notice I had the 2 times the 4 here, and the negative 1 times the 5 here, right? Just concentrating on the first column. Notice in the next column, my 4 and my 5 didn't change, right? I had the 4 and the 5 there as I went down. Okay. Let's go back to the system of equations here. Notice as you go from one equation to the next, that x and that y don't change, do they? Right? I've got a negative 1 times x. I've got a 3 times a y. In the next equation, my x and my y are the same. It's just the numbers that have changed, right? So what we can notice here is on the left-hand side, I can think of this as the product of two matrices. My right-hand one here is going to be my xy written vertically. Okay? If I'm going to write my xy vertically here, what numbers do you think I should put in this first row to make it come out to be negative x plus 3y? What numbers do you think I should have in that circled row to make it come out with a negative 1 times an x plus a 3 times a y? What do you think should go in there? Yeah, negative 1 and 3 here. Good. I should have a negative 1 and 3 here. All right. What numbers should go in the second row? A 5 and a negative 14. Good. Again, notice when you multiply, you'll have negative x plus 3y, which is exactly what we want on the left-hand side, right? On that first equation. And the other one would be 5 times x minus 14 times y. That's exactly what's on the left-hand side of that equation. Okay. I want to set this up as an equation. What do you think I should put on the right-hand side, do you think? Well, first let me ask you this. When I do that product, what size matrix should you end up with? When I do the product, when we get done, what size matrix do you end up with? A 2 by 1, right? So on the right-hand side, there better be a 2 by 1 matrix, right? What numbers do you think should go in there? 6 and negative 2. Good. I need a matrix equation. Remember, for the equation matrix, two matrices to be equal, the entries have to match, right? According to the system we have, I want this entry to match that entry, this entry to match that entry. So I'll have that on the right-hand side. So this is all we have to do to write a matrix equation. Write a system of equations as a matrix equation. Okay. So let's look at the next example. What size matrices? Well, first, if I make a column matrix here where the variables are, what variables should we use here? x1, x2, x3. Because those are the variables that are in each equation, right? Just matching it up with what we did in the first example. What do you think is going to go across the first row? Good. 2, negative 1, 4. Notice I better have 3 columns, right? Because the vertical matrix that I wrote on the right has 3 rows, and number of columns has to match number of rows. Right? And again, I want to end up with 2 times x1 minus 1 times x and a 4 times x3. Sorry. 2 times x1 minus 1 times x2 and a 4 times x3 there when I'm done, right? What do you think the second row should be? We're negative 1, 8. And the third row should be? Right. So notice all we're doing is pulling off the coefficients, right? And then on the right-hand side, what should we have? Good. And those should be the constants on the right-hand side. Right now, like I said, all we're doing is practicing getting into this form. We'll talk about why we do this here in the next section. All right, you tell me the next one. What should be the big matrix first? Okay. Okay. Good. Those are just the coefficients on the x1, the x2, the x3. And in particular, that next matrix on the right there should be x1, x2, x3. Good. And then finally, on the right-hand side should be 2, negative 1. Good. Bless you. What questions do you have on this? Is this okay? All right. Let's look at this application here, the problem real quick. Not to worry too much about what's going on in the application to start with, but let's ask a question first. First, could you even do B times A in this case? Can I take the B and multiply by the A that you're given? No. B has 2 columns, A only has 1 row, right? Okay. So regardless of anything else, regardless of the context of the problem, we can't do BA. We could do AB. So let's do AB. And then we'll worry about the interpretation in a little bit. And give you a little bit of insight why we care about such things. Okay. First question, what size matrix are you going to have when you're done? I agree with the by 2. It'd be a 1 by 2, right? Because we got 1 row in the first matrix and 2 columns in the second one. So we'll end up with a 1 by 2 when we're done. What's that first entry going to be? Six times 2,000 plus 10 times 3,000, good. Plus, good. Plus, good. That'll be the first entry, right? Again, we're taking row times the column that way, right? Okay. How about the second entry going across here? Running out of room. The 6 times the 2,500. Good. Good. So then we can simplify this. What do we get? 40. I don't feel like doing that in my head. So let's see how the calculator is for. So we got a calculator. You want to get a value yet?
105,000.
So what did it say?
105,000.
For the first one? Okay. Did you get the second one? No. Okay.
Should be 58,000.
58,000? What you said? Okay, cool. All right. All right. So the problem asks us to interpret what's going on. So let's think back to what's going on with the problem. The A matrix here is representing the number of cans, the number of ounces that each particular type of can holds, right? So a small can holds 6 ounces, a medium can holds 10 ounces, large can holds 14, giant can holds 28. The B matrix talks about how many cans of sauce are made and then how many cans of paste are made by size, right? So if we're doing this product and adding it together, what do these numbers at the end match up with? Say it again? The sauce and paste, and what quantity is it? Just how much it is, right? So this says that 105,000 ounces of sauce were made and 58,000 ounces of paste were made. That's what this is telling us, right? Because this is number of cans times number of ounces, number of cans times number of ounces, right? So you're getting total number of ounces in each one and you're adding them together, right? So that's what's going on. This is total number of ounces of sauce is in the first entry and total number of ounces of paste are in the second one. What questions do you have on this example? All right. We're going to start the second to last section of the semester today. Whoa. Well, I know, just 2 more to go. We're almost done. We're getting there. All right. So today we talked about multiplying matrices. How do we undo multiplication of numbers? What do? Division, right? So we don't really divide by matrices. We multiply by the inverse of a matrix. So that's what we're going to talk about today. Apparently I didn't add that in. Let me do that real quick. Let's see where to print out. Oh, sorry. Apparently I didn't put this in here. I thought I did. So today we're going to talk about inverses. Now remember, one of the reasons why we talk about division is because we're trying to undo multiplication. Right? One of the reasons why we do division is because we're trying to undo multiplication. In particular, if you were to try to solve the equation 3x equals 9, what do you do to get rid of the 3? Divide it by 3. Why? Because what do you want this coefficient on the x to be? A 1, right? The reason why we want the coefficient to be a 1 is because 1 times x is just x, right? It's what it means to be the multiplicative identity. It doesn't change it when you multiply by it, right? So we want a similar thing for matrices. So when we have what we refer to as the identity matrix, what we mean by the identity matrix is it's the n by n matrix with ones down the diagonal. And zeros everywhere else. Okay, so just to write down what I mean by that, if I talk about the I2 matrix, that's a 2 by 2 matrix. Its identity matrices are square. When I say ones down the diagonal, remember when we did our Gauss-Jordan method and we were trying to get those stair-stepping ones? That's what I mean by ones down the diagonal. Okay, so I'll have a 1 here and a 1 here. And then zeros everywhere else, 0 and 0 here. Okay. So if I had my I3 matrix, I would have 1, 0, 0, 0, 1, 0, 0, 0, 1. So on down the line. If I had I4, it'd be a 4 by 4 matrix. Looks exactly the same. Okay. Ones down the diagonal, zeros everywhere else. Why do we want this matrix to look like this? Okay. All right, so let's say I wanted to take, let's do the I2. If I wanted to take the matrix 1, 0, 0, 1 and multiply it by the matrix 2, 3, negative 1, 5, what do I end up with? What would I multiply together to give you the first entry? I would take 1 times the 2 and 0 times the negative 1. 1 times 2 plus 0 times negative 1. The next one over would be 1 times 3 plus 0 times 5, right? The next one would be 0 times 2 plus 1 times negative 1. This one would be 0 times 3 plus 1 times 5. And what do I end up with? 2, 3, negative 1, 5. I end up with what I started with, right? It's like multiplying by 1, right? That's why we want these identity matrices. It behaves like multiplying by 1. Okay? So when you, just to write that down, if A is an M by N matrix, then I times M, or I sub M times A will give me A, and A times I sub N gives me A. Now I have to make sure I have the right sizes. That's why I changed my subscripts, right? Remember, number of columns in your first matrix has to match number of rows. So I'd have to use IM in the first one. Number of columns has to match number of rows. That's why I had to use IN in the second one. But that's why we talk about the identity matrices. Now again, how do we get back to the identity? Remember when I mentioned above, if you've got the equation 3x equals 9, I need to divide by 3 or multiply by 1/3, right? Right? These two numbers here are called inverses of each other, right? It's what gets you back to the identity. Okay? So we have the exact same definition for matrices. We say that A is invertible or A has an inverse if there exists a matrix B such that A times B is the identity and B times A is the identity. It's what you multiply by to get back to the identity. That's what an inverse is. All right, so, good grief. So let's look at an example here, and then we'll do more of this next time. Let's multiply these two matrices together. And I know I'm going to do it relatively quickly since we got about 1 minute here. We're going to do 8 times 2 plus 3 times negative 5, right? That's the first entry. The next one will be 8 times negative 3 plus 3 times 8. The next one is 5 times 2 plus 2 times negative 5. And the last one is 5 times negative 3 plus 2 times 8. And if you simplify that, otherwise it'd be a very terrible example, I get back to the identity, right? Okay. You can show that it works the other way around too. If you reverse them, you'll get the identity. So what that means is that these two matrices are inverses of each other. So what we'll talk about on Friday is how do we find inverse matrices. I gave you examples of inverses, but we'll talk about how we actually find these, and that's what we'll concentrate on Friday. All right? Have a good one. We'll see you then.